All right, so today we're looking at the limit definition of a derivative and what a derivative represents, like graphically. So first of all, we're gonna look at a point. Let's call this point P, for example, and we can have this point at x. Its x coordinate is x. Let's just say that. So that means that its y coordinate is f of x. And so what the goal of the derivative is really is finding the slope at a specific point. So let's say at P. So how we can do this is we can set up another point Q, some distance h away from x, so we can call this x plus h, where h is the distance on the x-axis here. So this is h, and that corresponds to a y value of f of x plus h. So now we can put a line through these 2 points, and this would be something called a secant line. It's like this. It's just a line passing through 2 points. And we know that we can find the slope of the secant line by doing rise over run. And using our points, we have f of x plus h minus f of x over x plus h minus x. And if we simplify, this gives us f of x plus h minus f of x over h. So now this is the slope of our secant line, but we can see that, this is still quite far. This is still quite far from the tangent line of point P. So mathematically, how we can bring this secant line closer to our tangent line is we can move point Q closer towards point P. If you think about it, as they get arbitrarily close or close to zero, as the distance between them closes to zero, the secant line becomes a extremely accurate estimation of our tangent line. So mathematically, we can write this as the limit as h, the distance between the 2 points, approaches zero. The slope of the secant line is the slope at P. So the slope of the tangent line to P on this graph. This is also dy dx at P of x and f of x. Or we can call this f of P, f prime of P. So this is the notation for a derivative. And we want to do some examples, right? So we can consider the simple function f of x equals x squared. And this function, this is called the difference quotient. Yeah, so just keep that in mind. So to find the derivative of f of x, which is the slope of the tangent line to any point with x on the graph, we can use our limit definition. The limit as, so f of x plus h would be x plus h squared minus x squared all over h. And note that we have to keep writing the limit symbol until we plug in or substitute the limit in. So we can expand our square term. So this would just be x squared plus 2xh plus h squared minus x squared over h. And we can simplify this by getting rid of the x squared. So it's 2xh plus h squared over h. So if you notice that if right now we take our limit of h going to 0 and we substitute that value of 0 into our equation, we would just get 0. And that would not be useful for us, so we want to simplify this further. So we can take out h as a common factor. So we'd have h times 2x plus h over h. And we can take this out, leaving just 2x plus h. And now we can substitute our limit, which says that as h approaches 0, what does this function approach? Well, if h goes to 0, only 2x is left. So our function is 2x. So this is the derivative of f of x at any x, or d f dx, or you can call it dy dx if y equals x squared. So what this means is that, well, if we look at our graph x squared, at any point, okay, let's say this point, the slope of the tangent line, which is a line touching the point exactly at one point, the slope of this would be 2x if the function is x squared. And this is true for, for any slope. So if this was negative 4, then this would be 2 times negative 4 equals negative 8. So that's the slope for any point on x squared. And yeah, that's the limit definition of the derivative and a simple example.